Welcome back to the latest episode in our nuclear fusion odyssey. Are you all still with me? I published an article recently over on Singularity Hub where I write about science and technology about a new spin-out startup out of MIT that was hoping to make nuclear fusion a reality in the next 15 to 20 years. Naturally, the comments I got were mostly, "We've heard that one before." If nothing else, I hope that this series demonstrates that yes, I too have heard that one before. The title for this episode is Simple Engineering Problems, and it's inspired by a quote from Dr. Michio Kaku, who writes wonderful science communication books and built a particle accelerator in his garage as a teenager. He said, "What we usually consider impossible are simply engineering problems. There's no law of physics preventing them." I think this rather summarises the optimism that goes into fusion research and design, but in this episode we'll get into why simple engineering problems is a phrase that should turn your head. There was another notable shift in the 1970s that perhaps speaks to the optimism in the magnetic confinement community. After the very earliest excitable experiments had died down, people working on fusion would always phrase their latest device as a step along a road to achieving fusion someday. They weren't aiming to study the practicalities of harnessing fusion energy. They certainly weren't trying to build a working power plant. Instead, each new machine was an attempt to learn something more about fundamental plasma physics. They wanted a proof of concept, to prove that magnetic fields really could confine plasmas for long enough to produce net power. After all, why bother building a reactor when you're not even sure that you have a net power source? But in the early 1970s, more attention began to be paid to reactor studies, trying to work out how to harness the energy that was being produced by nuclear fusion, all in the same system. Because it's not just enough to have a very simple break-even reactor where the fusion releases more energy than is put in. You have to work out whether you can release more energy that can then be harnessed usefully than you put in whatever form you put it in, if that makes sense. So, for example, if you have a reactor that produces 150 megawatts of power for every 50 megawatts you put in, but then you lose a third of it in converting it back to electricity, then it's not actually gaining any net power. At the start of the decade, a conference was held in Culham in Oxford to discuss this reactor component of the fusion system. In essence, it seems like a fairly simple proposition. In a nuclear fission reactor, which had already been used for decades at this point, what you have is essentially hot neutrons and radiation produced when the uranium atoms split and undergo a chain reaction. You pump coolant through the reactor, which heats up, generates steam, and that steam then spins a turbine. So far, so good. Nuclear fusion should be a fairly similar proposition. Once you've got the plasma burning, it will emit energy as the nuclei fuse together, mostly in the form of extremely hot neutrons. You'd hope that a new heat source like this could more or less seamlessly replace heat from burning coal or oil or nuclear fission reactors. But it's not that simple. For a start, power plants are not particularly efficient at converting heat into electricity, because the fundamental laws of physics prevent you from doing this very efficiently. In your average fossil fuel power plant, less than a third of the energy released when coal or oil or natural gas is burned ends up as useful electricity. These are plants that have been optimised to within an inch of their lives, designed and improved for decades. After all, every fractional increase in percentage it translates to millions of dollars for the companies that run and operate them. But you can't beat the laws of thermodynamics, and it's very difficult to achieve extremely high levels of efficiency. In some ways, though, it's not a huge problem for fossil fuel and nuclear fission plants. If you need more electricity to be produced, you can simply build more power plants or burn more fuel. But fusion reactors obviously require a certain amount of energy to get going in the first place. If it works out that with your current design you can get 3 times what you put in, but then the simple tried and tested conversion stage from heat to electricity loses 2/3 of that again, then operating the magnets, heating the plasma with electricity, you don't gain anything at all. You're just burning fuel to send electricity on a majestic loop that allows it to fuse nuclei to produce that same electricity again. Which is a fun novelty, I suppose, but hardly limitless clean energy too cheap to meter. This means, of course, that you need to have a reactor of a certain size if you're going to produce more power than you put in. If the absolute minimum you can get fusion running for is 50 megawatts of power, then you probably need it to produce 500 megawatts of energy before it's going to be worthwhile. So there's a minimum size to the fusion plant that you can possibly have, whereas that's not necessarily the case with a fission plant. There is, of course, another problem. When I casually say hot particles, I mean neutrons that are flying off the deuterium-tritium fusion with an energy of 14.1 MeV. That's 14.1 megaelectron-volts, equivalent to the energy released if 30-odd pairs of electrons and positrons annihilated each other. So in terms of a temperature equivalent, those neutrons are 160 billion degrees Kelvin. They're moving at around 100 million miles an hour. And what's more, because they're electrically neutral, you can't use electrical or magnetic fields to easily slow them down. What these neutrons tend to like to do is crash into and upset the nuclei of atoms. Anything they do crash into quickly becomes radioactive, which means that fusion plants do in fact produce radioactive waste. Instead of waste fuel, however, like in a fission power plant, it's heavily irradiated bits of the plant itself that will likely have to be periodically disposed of before they break entirely. But if you want to harness their energy, at some point, these scorching hot neutrons, hotter than the heart of the sun, will have to crash into something and give that energy up. Even today, a huge area of fusion research is simply trying to find materials that can withstand bombardment from these incredibly hot neutrons for any reasonable length of time, so that they can be directed where you want them to go. So suffice it to say that as well as being an immense physics challenge to confine plasma with magnetic fields for a long enough time to generate energy, there are also immense fusion engineering and design challenges to overcome if you want a reactor that works, that's stable, and that will produce a decent amount of energy without constantly breaking down, requiring new parts, or needing more energy than it generates. As Joan Lisa Bromberg points out, there's a different kind of engineering required to create something that's purely experimental apparatus and something that's designed to generate a steady stream of power. A key aspect to experimental design is to minimise the time between coming up with the idea for your experiment and being able to perform it. After all, there are competing groups, and if your kit takes 10 years to build, people might have answered the questions you had by some other way in the interim. So the experimental tokamaks and laser fusion setups that were created were built with simplicity in mind. You go in, run a few tests, get the results as quickly as you can. If the machine fails after a few years or only gives reliable results every third run, it's no great loss. The same can't be said of a power plant. It needs to be commercially viable, and it needs to be competitive with other means of producing electricity, so it has to work continuously for many years. And fusion engineers would also start making demands of the physicists. If some brilliant plasma theoretician comes along and says you can obtain optimal fusion conditions by heating the plasma to 1 trillion degrees Celsius, and that happens to be hot enough that the breaking radiation from the accelerating charged particles would melt your power plant, it's obviously not an optimal solution. Engineering and the practicalities of getting something that will work as a reactor and isn't just a bomb of some kind is going to be a limiting factor on what types of fusion you can approach. This isn't just some idle complication either, because you can't just wave your hands and say, oh, by the time fusion scientists have figured out how to get the plasma to behave and release energy through fusion, the engineers will have figured out how to harness its energy. That's the easy part. Because it can fundamentally alter how feasible fusion is as a source of energy. We're used to hearing this mantra that fusion is a source of clean, safe, limitless energy. Seriously, just out of interest, I googled the phrase clean, safe, limitless power, and you get pages and pages of articles about nuclear fusion, from private companies like Tokamak Energy and universities like UC Berkeley. Star power on Earth, a limitless clean energy future. We are closer than ever to unlimited clean energy. Clean, limitless fusion energy is just 15 years away, say MIT. I even wrote an article myself, as I mentioned, for Singularity Hub, about that latest spin-out company from MIT, which acts as a very brief history of nuclear fusion. These claims sound wonderful, and of course they're designed to ensure that people will continue to pour millions into your fusion research problem. And in some ways, you can justify them. Fusion energy is limitless, in a sense. Fossil fuels are running out and will be gone over a timescale of decades to centuries at most. The uranium that we mine for our fission reactors is also finite, formed by the neutron star mergers billions of miles away, and finding its way into the Earth's crust. If we started using that on a larger scale than we do, then it too would run out within centuries. Trying to figure out how much uranium we have left is very similar to trying to figure out how much coal or oil is left, and you'll remember in the Teotwalki episode Peak Oil, we pontificated about how difficult that is. Yes, it's true that extraction technologies get better all the time, but it's also true, regardless of how the economists might attempt to spin it, that the stuff is finite. There are a few arguments that annoyed me more than this. Oh, oil will never run out because of supply and demand. We'll always be able to sell the last drop of oil for some price, and new technologies will let us make more for any price. The chief economist of BP argued this, saying that even the desk keeper's writing act could be turned into oil if someone was willing to pay the price. I fail to see how this is a valid argument, in the same way that if I was serving cake at a party and had too many guests, my reassurance is that I'll just serve everyone a crumb and charge 50 quid each and then we won't run out, and when we run out of crumbs I guess people can eat the tablecloth. It's not a good argument. Okay, I'm just going to calm down on that for a second. Based on your assumptions about how much better those techniques will get, and based on your assumptions about how much energy we'll use in the future, etc., we don't know how long uranium will last, but at the current rates of use, the proven recoverable uranium reserves will last for around 135 years, similar to some estimates for coal. So on a timescale of a few centuries, if we keep consuming energy the way we do, fossil fuels and uranium may well both become impractical. So the claims that nuclear fusion is limitless by comparison rest on the idea that you'll use deuterium as the main source of the fuel. So you can't have these deuterium-tritium reactions that things are actually using. You need deuterium-deuterium reactions for this to be real. Deuterium is just heavy hydrogen, and it turns out that 1 out of 5,000 seawater molecules are heavy water. So you can make all kinds of nice statements along the lines of 1 litre of seawater contains more fuel than 500 litres of petrol, or the fuel for nuclear fusion is just seawater. Yes, once you've actually extracted the deuterium, that's more or less right. The idea that the fusion fuel is simple seawater is also behind some of the more absurd claims you'll see that fusion energy is somehow also free. I mean, fairly reputable websites will still publish this amazing claim, with TechRadar billing fusion as unlimited free energy. I mean, it's free in the same way that a house is free to live in once you've bought it and paid your electricity bills for the month. Or perhaps more pertinently, in the way that energy from a wind turbine or solar panel is free once you've built them and paid for their maintenance costs. Funnily enough, you still get charged for electricity from solar panels. It's not free. The people currently building the multi-billion-dollar ITER reactor will assure you that any energy it does produce was certainly not free. Nevertheless, assuming that you can extract the deuterium from seawater, the theoretical maximum that we could use looks more like billions of years of current energy use as opposed to the centuries provided by fossil fuels. That's the same kind of timescale that the sun is going to exist for before it expands to roast the Earth. So, to all intents and purposes, one would hope that this would solve the energy problem in the sense that it wouldn't run out. It's as much as you could ever want. But this assumes that you get the deuterium-deuterium cycle of fusion working. At present, the big fusion projects like ITER are going with deuterium-tritium fusion, which we explained in previous episodes is cheaper to achieve. Tritium has a half-life of 10 years, which means that it doesn't really exist in the Earth's crust or seawater in the same way as deuterium does. It just decays too quickly for that. The way that it's currently produced for these fusion experiments is creating it by bombarding lithium with neutrons. Luckily, as mentioned, the fusion reactor produces a great deal of neutrons. So one thing you could think of doing is using lithium as a coolant for the reactor. You swill it around the fusion reacting chamber in liquid form. Then it gets bombarded by energetic neutrons, and it splits into deuterium and an isotope of helium. This is good because it means you don't need to expend too much additional energy to make the tritium. It's a byproduct of clever reactor design. But then, of course, the inputs to your system are deuterium from seawater and lithium from mining. Lithium is also a finite resource, and ever more finite as lithium-ion batteries grow more popular. We can imagine that if the world does start to move away from fossil fuels, things like solar plus storage or wind plus storage will be useful, and given that even the next generation batteries may use more lithium still, there might be only 120 to 150 years of lithium left in the ground, based on current consumption patterns. Now, it's true that there is a great deal of lithium in seawater also, and that extracting it is a bit of a holy grail of resource extraction science. For example, right now, China has more or less cornered the lithium market, buying up lots of shares in mines in South America. Western powers are looking to their own deposits to extract them, but large-scale lithium mining is pretty expensive and environmentally destructive by itself. It's not the kind of thing that you could get planning permission for that easily. What's more, the lithium breeder fusion reactor has its own issues. Even though it looks like an appealing solution that will provide you with all the tritium you need, it's not exactly self-sustaining. Daniel Jaspy, who worked on nuclear fusion for more than 25 years, wrote an excellent article highlighting some of the technical shortfalls with these ideas in the Bulletin of the Atomic Scientists. He points out, quote, "The tritium consumed in fusion can theoretically be fully regenerated in order to sustain the nuclear reactions. To accomplish this goal, a lithium-containing blanket must be placed around the plasma. But there is a major difficulty. The lithium blanket can only partly surround the reactor because of the gaps required for vacuum pumping, beam and fuel injection in magnetic confinement fusion reactors, and for driver beams and removal of target debris in inertial confinement reactors. Nevertheless, the most comprehensive analyses indicate that there can be up to a 15% surplus in regenerating tritium. But in practice, any surplus will be needed to accommodate the incomplete extraction and processing of the tritium bred in the blanket. Replacing all the burned up tritium in a fusion reactor, however, addresses only a minor part of the all-important issue of replenishing the tritium fuel supply. Less than 10% of the injected fuel will actually be burned in a magnetic confinement fusion device before it escapes the reacting region. The vast majority of injected tritium must therefore be scavenged from the surfaces and interiors of the reactor's myriad subsystems and re-injected 10 to 20 times before it is completely burned. If only 1% of the unburned tritium is not recovered and re-injected, even the largest surplus in the lithium blanket regeneration process cannot make up for the lost tritium. By way of comparison, in the two magnetic confinement fusion facilities where tritium has been used, Princeton's Tokamak Fusion Test Reactor and the Joint European Tourist JET, approximately 10% of the injected tritium was never recovered. So in practice, Jaspy is pointing out that even if your supply of lithium for the blanket is limitless, it can still only make up for a small amount of the tritium that's being used. You need a really efficient system to recover the unburned tritium, injecting it into the reactor over and over again. Jaspy doesn't think this is really practical, so instead, he says, to make up for the inevitable shortfalls in recovering unburned tritium for use as fuel, fission reactors must continue to be used to produce sufficient supplies of tritium. A situation that implies a perpetual dependence on fission reactors with all their safety and nuclear proliferation problems. Because external tritium production is enormously expensive, it is likely instead that only fusion reactors fueled solely with deuterium can ever be practical from the viewpoint of fuel supply. Jaspy's might be a pessimistic view, one that relies on us cracking deuterium-only fusion as well as deuterium-tritium fusion as the only really scalable solution, or else keeping nuclear fission reactors around to produce expensive tritium as fuel for fusion reactants. But you can see that even in this there are some pretty big potential asterisks to the idea that power from nuclear fusion is effectively limitless. It is, providing we develop new ways to extract the relevant fuels, or else master the more difficult form of nuclear fusion, which could take even longer than getting deuterium-tritium fusion to work. Another major downside that particularly bugs magnetic confinement fusion is in what's called parasitic energy consumption. In other words, nuclear fusion reactors need power to work. The magnets that confine the plasma need to be cooled with liquid helium, you need to pump the coolant around, you need a good vacuum pump to evacuate the chamber where fusion is taking place, you need to process the tritium and deuterium to provide fuel for the planet, you need to air condition the buildings, etc., etc., etc. These energy costs take place constantly, regardless of whether or not the plant is currently producing energy, so you can multiply it by whatever fraction of time your power plant is out for. If you have a 2-week outage, that's when the power plant is just a drain on electricity from elsewhere, rather than producing anything in the net. And while a plant is running, in a tokamak, you heat the plasma by driving a current through it, which requires more energy. The point here is not that you can't ever reach break-even. The point is that with current physics and engineering knowledge, you need a huge device just to generate more energy than is consumed by running it. Generating 1 megawatt more than you consume is obviously not economically feasible if your plant costs $20 billion to build. Why not just build some solar panels instead? So you need a really huge device that will generate a substantial amount more energy than is consumed. According to Jaspy, this means that the smallest fusion reactor that's commercially viable is probably around a gigawatt in size. And indeed, if you look at the mainstream plants for tokamaks at present, ITER, which is supposed to be the first fusion reactor to produce more energy than it consumes, is slated to produce 500 megawatts of power. But DEMO, the hypothetical plant that follows ITER and is supposed to be the first practical working nuclear power plant using fusion, is slated to produce 25 times the power required for break-even, and exist on a scale between 2 to 4 gigawatts of power. By comparison, the largest coal-fired power plants in China and South Korea are between 4 to 6 gigawatts, and they are behemoths. So in other words, the moment you decide to get power from nuclear fusion, unless you have some new technology that goes against the current ITER demo orthodoxy, you're committed to building one of the biggest power plants in the world, with some of the most expensive and complicated equipment, and a huge capital overhead that you have to pay down before you have any energy being produced at all. Unlike coal-fired power plants, you can't build it in pieces and just add more generators when you need to. Unlike my beloved solar panels, you can't just throw a few down wherever you have some spare space for limited money and then chuck them onto the grid, or even build them on the roof of your house. It's all or nothing, and all is a lot. Next time we'll go further into the depressing mire of reasons why fusion energy might not be clean, limitless and cheap after all, and I hope by the end of that you'll really question why it is that people are allowed to repeat these claims endlessly when they talk about nuclear fusion and not any other fuel. You've been listening to Physical Attraction. You can visit us on the web at www.physicspodcast.com, where you'll find the contact form, opportunities to donate to the show, and of course the archive of all of our 100 plus episodes that have been released so far. You can contact us on Twitter at PhysicsPod. You can follow us on Facebook at Physical Attraction. You can support the show through donations, but the best way to support the show is by either reviewing us on a public place or telling as many of your friends who might want to listen as possible. If you all tell one other person, the audience increases exponentially, and we'll probably have enough to crowdfund our own fusion reactor at some point in the future. Until next time then, take care.
Thank you.